Welcome back. So we are now going to start a new part on a new data shape. So I told you at the start of the lecture, there are actually several data shapes and tables that we now know almost by heart, how tables look like, what the relational model is, what the relational algebra is, the query language to define tables, to query tables, to index, and so on. So we know tables very well. It turns out that tables are only one of 5 data shapes. This is the oldest one, the one that mankind has known for thousands of years. So it's one of the most natural data shapes. But there's also cubes, trees, graphs, and text. We are going in this lecture, actually in this next series of slides, series 9, to look at cubes. Why cubes? Because they actually are a bit similar to tables in some ways, especially they can be stored in tables very easily. And the other advantage is that even though there is a language also for querying cubes, we can also use SQL. So it means that you won't have to learn a new language. We would just use SQL to query cubes as well, right? But it's a different mindset, a different way of thinking. And for trees and graphs, this is something that we do in Big Data for Engineers. So this is going to be next spring because these are data shapes that are a bit more recent. So there's a lot of databases that support them, but it's more recent, and tables date back to the 70s. And finally, text is information retrieval. It's basically about a search engine, right? Okay, so let's get started. So cubes are actually very connected to the notion of analytics. It is something that is very popular in a lot of companies because when you have all of your sales data, for example, in a company organized in cubes, in what is called the data warehouse, then you can, even with Excel, with some spreadsheet software, you can produce this sort of very fancy graphs that you then show to the CFO, CEO, and so on. So this is one of the reasons why they are so popular. Even though they are a bit more recent than tables, all right? So historically, let me give you a very quick, but it's much, of course, shorter than in the introduction to this lecture. We had what could be called the age of transactions, starting from the 70s, because you know that 1970 is the year 1 of databases in the modern way. So 1970s all the way to the 2000s is the age of transactions, because when you have a relational database, you keep inserting and deleting and updating and also querying in it. So you do a lot of transactions. Well, there was actually a turning point in the 90s. This is where business intelligence started to become something. And a lot of companies started being interested in analyzing their data in order to make decisions based on that, especially sales data, which is the main use case. So there started the age of business intelligence. In this year. And then in the 2000s, this is the age of big data. This is what I told you about trees and graphs. So the trees and graphs actually emerged there, but also tables are still important, but then with billions of rows. And this is something you do totally differently than what we've seen in this lecture with PostgreSQL, right? But again, this is for spring. This is big data for engineers. Today, we are going to look into this business intelligence and cubes. So OLTP, sounds new. It's actually not. It's what we've been doing since the start of the semester. It means online transaction processing, and it's PostgreSQL with select from where and insertion, deletion, updates, and so on. It's everything we've been doing so far falls in that category. In the other category, we have OLAP. The only difference is it's online analytical processing. The difference is the use case. And I will tell you about the differences between the two, contrast them so that you understand well the difference between the two. But again, it's only the third letter that is different. So here, online transaction processing, online analytical processing. And this is where cubes actually come into play. This is where tables come into play. Even though I have to warn you, it's not a strict mapping that here it must be tables and here it must be cubes. You can also imagine OLTP with other things than tables. You can also imagine OLAP with other things than cubes. But very generally, a lot of people tend to imagine a relational database when they hear OLTP, and they tend to imagine a business intelligence system with data cubes when they think of OLAP. All right, so these are two paradigms. And again, we've been doing that so far. And today, we are going to start looking into this one. So what is OLTP? It's the consistent and reliable record keeping. So you want a database that stores your data, that you can modify, update, insert, delete, that you can query, and that is reliable. meaning, for example, there's these transactions that we've looked into with serializability and so on, that even if there's multiple users, it makes sure that they do not see each other, kind of isolates them from each other. It also makes sure that unauthorized people do not have access to data they shouldn't have access to, and so on and so on, right? So this is why we have a whole relational database management system that takes care of all of it for you. And this is why it can be very expensive. It can easily cost 100,000 francs for a license of one of the full-fledged relational database management systems, but they are extremely powerful. And so they allow you to keep track of your records, and this is done in a way that you can constantly update them, right? So it's like you're an online shop, for example, and you have to update your inventory all the time whenever people buy, whenever people use your system, and so on. So it's a constant updating of the system. A lot of transactions, we've seen that. So what is a transaction? Again, a transaction is just a sequence of queries that can be updating or reading queries. So a transaction is a sequence of queries, and it's a small portions of data very often. So we've seen with indexing full scans versus highly filtering queries, right? Well, it turns out that the highly filtering queries are actually occurring much more often than full scans. First, because full scans are a bit slower, but the highly filtering queries, if you think of an online shop, that's what it needs. Because when a user is trying to look up a certain book or a book with a certain author, or you're looking for the specific orders of one customer, then in the gigantic database of all customers, what you really want is only the information of one customer that you are going to display on the page. So you can see that a lot of the queries that are executed from the website of an online shop, like Digitech, Amazon, Copatome, I don't know, it's a lot of highly filtering queries like that. So small portions of the table at a time, either to read or to update, and full scans a bit less frequently, right? So this is the use case of what we've been doing so far, even though we also saw grouping queries and order by queries, but knowing that the select from where is really the one that wins. A lot of transactions, furthermore, not just one, but a lot of transactions, because your website might have millions of customers visiting it at the same time, and you have to be able to answer all of these queries. So a lot of transactions, but they are all executing on a different section of your table, on small portions of the data. We've also seen that the data in OLTP is normalized, and we've seen the first normal form with atomic values. It's the atomic integrity that we also called it. And we've also seen the Boyce code normal form, which is a way of avoiding, as you might remember, update, insertion, and deletion anomalies. This is what we want to avoid. And it makes sense, right? Because I've just told you that we have millions of people constantly writing to the database and reading from it. So you see that normal forms are extremely important for this reason. So this is why we normalize the data. We have normalized the data in Boyce code normal form. There's others, of course, other normal forms than Boyce code, but for the purpose of this course, it's basically Boyce code. All right. On the other hand, online analytical processing is different. It's meant to do decision support. It's basically the report that you bring to the CEO, and then they will see the fancy pie charts and decide on that, right? So it must be based on data you analyze, and it's decision support. So of course, the requirements are a bit different. The first thing is that you need to read very large portions of the data, right? Because if you look, for example, at all the sales that you've had this year, or maybe in the last 10 years, you want the report and the pie charts to include a large portion of the data. Of course, it doesn't mean that you are going to throw a report with a million pages to the CEO. Of course, it's condensed, right? You have aggregated the data in such a way that it can be read and understood more easily, right? But it comes from very large portions of the data because you aggregated over the entire set of data that you're interested in. Possibly many joins, because you might need to relate data to each other, like customers and orders and the inventory and so on. So possibly many joins in there. It's very heavy. You know that joins are a bit slower to execute. Selection projection can be faster, especially with indices. But if you try to join, especially Cartesian products, it's extremely heavy. Group by also takes time in order to do it. We know how to execute them, of course, efficiently, but it's still slow, right? All right, so this is different. Here are a few examples. We have web analytics, like your web server report with all the excess that there was. You can actually analyze it as OLAP. It can be very large if you are a very big company and you have a billion visitors. Sales analytics, this is the #1 use case. This is actually how things actually were born on the OLAP side. That was the main driver. Management support on some other aspects, statistical analysis like the census, for example, in the US every 10 years. This actually even started I think more than a century ago, this thing actually with IBM and the very first pre-computers that were already invented in order to solve that sort of issues, even before we had the transistors and silicon-based computation. So this is actually more than a century old, older than the modern computers. Then, of course, scientific databases, bioinformatics, DNA, and so on, right? Okay. So you can see that here we are looking at detailed individual records for OLTP, but on OLAP, we are talking about summarized consolidated data that might come from millions of records, but condensed into a fancy looking report. So again, I'm repeating because it's very important that you basically understand that. Lots of writes for OLTP, a lot of transactions, people writing to the database. This is why we need the normal forms. OLAP, on the contrary, is a lot of reads. The data is there, you dump it, right? You have the data, that's what you had in the last 10 years. What you need to do is analyze it. So you need to read it and aggregate it and use it, but this is about reading the data when you do this sort of reports, all right? So on OLTP, you have small sets of records. On OLAP, you analyze on very big chunks of data, so several years, an entire region, you know, this sort of things. Another aspect is that OLTP tends to be fast. Well, we've seen how with indices, hash indices, B-tree indices, and so on. This is how you get very interactive response time. So now you understand how an online shop, even though they have billions of articles in their inventory, when you load the page, it's instant. Why? Because they have indices. This is exactly what the benefit of having an index is, why the page shows instantly when you look up for something in an online shop. And then OLAP is slow and interactive in the sense that it might take hours in order for a query to completely execute, or even days. So you basically type it in, and then you need to let it run in the background and then come back later. So it's absolutely not the same experience that you have. So you're not going to offer an OLAP online live analysis on your website, because people would have to stay for hours in front of their screens until it's ready, right? So for a website powered, for a database powered website, it's really on this side, again, OLTP. Another aspect of the difference between OLAP and OLTP is that for OLTP, we like consistency. You remember ACID, these 4 letters that I gave you with the transaction, so atomicity, consistency, isolation, and durability, the 4 things we want to achieve. So we need consistency. This is also, again, a motivation for normal forms. The update anomalies destroyed the consistency, right? So when we had data that was stored at multiple locations, if we update it at one location, then we get inconsistent in the database. If you have a normal form, it no longer happens. So you want consistency with OLTP. Do we have a question?
Yes. So can't we have indices or something similar in OLAP to make it faster?
We can also organize things that make it faster and more efficient. But the goal is not to be faster as in milliseconds fast. That's not the goal. All right. And of course, just to add, these are 2 extremes, right? Of course, you also have use cases that might be a bit more in the middle, right? So this is really to contrast two approaches and 2 use cases. But in reality, sometimes you might have a bit of this, a bit of that, right?
Okay, thanks.
Actually, if you look in the book, there are even, I think it's not part of the material that we include, but there are even in the book a few explanations on how you can build indices on cubes, right? But it's a little bit less of the first primary driver. It doesn't start with that, let's say. That's something that comes later for optimizing further. Is there another question?
No question.
No? All right, thank you. So we've seen that we need consistency with our normal forms, right? In such a way that we store the data just once to make sure that it's consistent, right? But on OLAP, it's different because we don't care about writing. We don't care about duplicates anymore because it's anyway something we do not touch. So we don't have the problem with update anomalies, insert anomalies, delete anomalies. It's a problem we don't have. So in OLAP, one of the ways to make it faster is redundancy. We just denormalize. We store it. We store it redundantly. We might store the same values at plenty of places because then we don't have to do joins anymore, right? If it's already pre-computed, it's a way of saying we pre-compute the joins. So this is why we have a lot of redundancy in OLAP. I'm not saying it's like indices, but it's a way, a bit like indices. It's a similar way of let's say, an alternate way of making queries faster, right? You can have indices, but you can also have redundancy. In a way, if I'm a bit provocative, an index is nothing else than redundancy. It is what an index is. It is redundant because you don't need it. It's just that if you don't have it, it's slower. But an index is just a redundant extension to a table that you can use to make it faster. So if maybe it answers the question you asked before, so this is not unrelated to indices, the idea of not hesitating to have redundant data in OLAP, right? So this maybe that's a connection as well. All right. So now a few fancy terms, 4 terms actually. A data warehouse, which is what you actually call, as opposed to a database, OLAP, it's typically called the data warehouse. It's a subject-oriented, integrated, time-variant, non-volatile collection of data in support of management decision-making process. So I basically threw all of that at you. It's these 4 words that are important: subject-oriented, integrated, time-variant, and non-volatile, right? This is something I already told you before. It's about making decisions. So I'm going to go through these 4 words here, one by one. Subject-oriented means that when you have a warehouse, it's typically a very specific kind of data. For example, on customers, on sales, on products, on events, and so on. So it's subject-oriented and tuned to a very specific use case. The second thing is that it's integrated. In many companies, they have a lot of databases, especially if the companies are even bigger, they have a lot of databases. They even have a lot of database vendors. So the same company might have PostgreSQL and also MySQL and also Oracle and maybe even NoSQL databases and so on. It's in a lot of companies, it's actually a mess. There are so many databases a little bit everywhere. Some of them might be maintained centrally, and then maybe some teams have their own computers with their own databases. And then the people from the support come to them and say, no, 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 you are not allowed to have your database here. You have to go through us and so on. So it's very hard to organize. When you're a company, you can very easily end up with a huge number of databases. And actually, these databases turn out in the end to be data silos, because then you have a lot of data that doesn't talk to each other, and the data is just compartmented. And when you start to want analyzing it, you realize you can't because it doesn't communicate. So it's very hard to do. So the idea of OLAP is to take all of that data that is spread all over the place in the company and to import it and integrate it into a single place called the data warehouse, typically in the form of cubes. In terms of data shapes. So this is the idea. And once you have poured all of your data in your data warehouse, then you can start analyzing it because you no longer need to worry about the borders between the data silos, right? So this is one of the ideas behind a data warehouse. So that was integrated. Now time variant. Time is very important typically in OLAP setups in the sense that we very often talk about periods. For example, companies think in years, in decades, in quarters, in months, you know. So typically on your pie charts, if you look at a financial report or a company report, it will be organized in months and quarters and years. So time is extremely important in these data warehouses. And every time there's a new year, you add new data and take it from there. It's not necessarily true in an OLTP setup with a relational database. You might not even have any mention of time at all in your database. It's just data. And then time is just implicit because the data keeps evolving. You insert, you delete, and so on. You might have databases that are able to keep track of the history of your data and no longer delete anything, but just remember how the data was before, but it's different. Here, it's really that the time, looking at the data from a time perspective in quarters, in years, and so on, is absolutely important in a data warehouse, right? Really think of the fancy reports that you see, the annual reports, even at ETH, that you see everywhere. There's always this time dimension with years and quarters, right? So very often you have the data, it's very often 5 to 10 years. Then after 10 years, there's different reasons why you don't look at the data anymore. Some of them are technical, some of them are political, some of them are legal. So there's plenty of different reasons. So very typically, you look at the past 5 to 10 years of data that you have, right? So legal in the sense that you're obligated to drop it, for example, can be technical because the technologies have evolved. And the data that is 10 or 20 years old is so different than the data today that you can not use it anymore. Maybe also you did not collect data back then that you started collecting 10 years ago. There's a lot of different reasons why there is this, but very often you look at the past 5 to 10 years, right? Non-volatile, in the sense that you basically load your data in your warehouse. It takes a lot of time, maybe hours or even days in order to do that, but you basically load it, you access it, and that's pretty much it, right? So you don't write to the system. The data warehouse is read-only. It's there, the data is there, you only analyze it and read it, but you do not update the data. The data is updated here. This is where you update the data in the original databases. This is just a copy that you make, right? So you load the data in there and you access it, and that's it. All right? Everybody following? Is there a question in the chat? You see?
No question.
No questions? All right, perfect. So what does the, I'm sorry, I don't know why my left and my right are a bit confused today. So as I said, it can be a number of databases that you have in your company that you read from. So customer relationship management, ERP, OLTP databases, some files. You might even have some files on your hard drive and so on. And basically what you do is there's a new word here called ETL. It's actually a verb, believe it or not. ETL is a verb, an English verb. So you basically ETL from all of the databases that you have in your company, you ETL it into the data warehouse, right? I will come back on what ETL means. Actually, it means extract, transform, load. So these are three things that you do, but people use it so often that they actually turned it into a verb. Okay, so you basically import it there, and then once you have your data warehouse, you can analyze the data. We'll see why cubes are so important. You can build reports, and you can also mine it with machine learning and all sorts of technologies that there are. So you see the analogy that I made here with here the wheat and the flour and the bread, right? So this is really a transformation in the value added, in the value added chain, right? So you start with very raw data, then you start deriving it and transforming it, and then finally you have this final product that is the fancy looking report that you have at the end, all right? I said something about redundancy. The idea is that we want to avoid redundancy in a normal relational database system because of, as we said, the inconsistencies, the anomalies that can appear when you start updating it. So we want to be normal form. Remember that as a rule of thumb, normal forms means more table. You try to spread your data over a lot of tables, and each table does only one thing, but it does it right. However, in the case of OLAP, we instead join them back, materialize them in a single or maybe a few, but materialized views. So this is not new to you. We saw these views, right, in SQL, and we saw that some of them can be materialized. So there's a good analogy to make here. It's really views on this data obtained via queries, but we materialize them in our data warehouse. And we are going to look at these materialized views when we start analyzing the data, and these are the cubes that we look at. Denormalized, why? Because again, the idea of normalization is to split. This is what we do when we have the Boyce Code normal form decomposition, right? We try to split the table into more tables. This is the opposite. We denormalize the data into these larger views, and we don't care anymore about if it's redundant or the same value is stored at multiple places. So again, this is just a reminder about the normal forms that The first normal form, that's the atomic integrity, is the idea that you forbid this sort of nested structures. We'll see them in spring, big data for engineers, but for now we forbid that sort of normal forms. Then this is just, it's not part of the course material, but I still included them because maybe that's a bit of bonus material for you if you're interested. So there's actually a second and a third normal form in addition to the Boyce code normal form. Let me very quickly tell you what this is about. Remember the functional dependencies? It's all about functional dependencies. So the idea of the second normal form is that that sort of thing is forbidden. You are not allowed to have, if you have a primary key here, for example, you have a primary key that consists of 2 columns. Again, it was a super key. That super key is minimal, so it's a candidate key. And then you say, okay, I take that candidate key as a primary key. And then you have it. So this is the primary key. In order to be in second normal form, what you forbid is a functional dependency for from part of that primary key. You're not allowed to have a functional dependency on less than this primary key. So this is forbidden. This would break the second normal form, for example. And the third normal form is a bit different. Here, what you forbid is to have functional dependencies from outside the primary key, right? So you see that whether it is the second, third, or Boyce code normal form, it's all about forbidding functional dependencies just in different ways. And remember that in the case of the Boyce code normal form, what we forbid and we do not want is a functional dependency that doesn't have a super key on the left, right? Again, but this is not part of the material. You don't need to worry about the second and third normal forms. I just wanted to show them to you because they are here, right? So these are the normal forms that we have. And so in OLAP, we just go the opposite way of this normal form. Instead of wanting higher normal forms, we want to denormalize into redundant materialized views in order to be faster to read, right? Because we don't need to join anymore. All right. So why do we need to materialize? It's, as I said, the original data sources, they can come from 10 different database vendors with plenty of different schemas. They might not even talk to each other. Some databases maybe have a Java interface, some others have a C++ interface, others have a language maybe other than SQL if they are not SQL databases. So it's so heterogeneous, it would be a nightmare to build a system, to build the reports from all these databases. That would be very hard to do. So this is why we want to materialize all of this data into a single place, the data warehouse, and everything is in that data warehouse.
Question. So to update our yearly average data with the latest quarter, we need to re-import everything into the data warehouse? Or is there a way to update the warehouse directly?
Well, you could figure out ways. I think it really depends on the use case, but you could also figure out a way in which you only every year, once a year, you update just the last year of data in the data warehouse. And I could imagine doing both. Some people may re-import absolutely everything again, because some of the data of previous years might have been corrected, right? It's possible that there's been amendments or fixes in past data, in which case you need to re-import everything. If you know that the data up to 1 year has not changed, then maybe you can only ETL, because that's the verb, ETL the past year and that's it. But again, you need to be careful. It's really not the idea that the data warehouse can be updated. That's really not the idea. You can ETL, you dump the materialized view in the data warehouse, but you do not update it, right? So basically doing increments or basically just adding 1 more year, that maybe you can do. That's a bit pushing it, but you can absolutely do that sort of things. But again, what's important is you don't update it. That's not the idea. All right. And again, imagine that this is something you do every year, once a year, right? If you produce your yearly, it's not something you do all the time. So this is why it's also fine that it takes a few days to re-import, right? Okay, but again, I'm cautious because it all depends on the companies, and people can have different approaches. All right. So I'm actually very redundant on my slides. I keep repeating the same thing, and that's exactly the same way that OLAP is redundant. So I'm basically being consistent with teaching OLAP here, right? But again, with repetition, I'm sure that you remember these things, right? So again, we derive the data into cubes. We do have, and that's actually referring to a question earlier, we might have special purpose indices that absolutely exist. They are described in the book, but I'm not focusing too much on them today. All right. So when we query OLAP, we can also offer access in some cases from 1 to 10 seconds. So what I have in mind here is that there's the data warehouse in the company, and some of the users of the company who have access to it might use a spreadsheet software that in some way they connect to the data warehouse, and in their spreadsheet software, they can do some queries, but whenever they click a button, the entire computer is going to freeze for 10 seconds or 30 seconds, and then the data appears. It's not like it's instant. So you really have to imagine your whole spreadsheet software is freezing for the time that it takes to actually get the result of your query. So this is what we call slow interactive. It's not the same experience as a SQL relational database shell when you have indices, right? And again, spreadsheet software is used a lot for doing that sort of things. Even though it's of course translated to SQL or something like that in the background, but a lot of people do it without even knowing these languages. And of course, so this is one way that you use OLAP, people sitting in front of their computers using spreadsheet software. Or you also have some continuous monitoring, tracking, report generation, and so on that can take hours, right? Some companies might want to monitor everything for all sorts of reasons, legal, security, and so on, right? So there's also a lot of technologies that allow you to do that sort of things. So now that's the final slide where I'm dumping everything exactly in the same way we ETL into an OLAP data warehouse. I'm dumping the summary of differences between OLTP and the OLAP so that you have an overview of that. So again, this is the original OLAP is derived. The purpose here is really like running a web shop, for example, business tasks, but here it's more decision support. In OLTP, we look at snapshots of the data where you always see the latest version of your database, right? Because you keep updating it, but you only see the latest version. In OLAP, you have a time dimension that you can go back in time for 10 years. When you write, you do periodic refreshes at best or a full reimport at worst, right? But you don't spend your time updating it. It's really just once in a while. You typically have aggregations in OLAP. You normalize in relational databases, but you denormalize in OLAP. This ACID thing, that's for the transactions that I told you about for when you don't want any issues with your bank accounts when people withdraw at the ATM, you need these properties. For OLAP, it's a bit different. What you need is more confidence intervals, it's fine to sample and so on. Serializability is what we saw that is important for OLTP. For OLAP, it's reproducibility. Because if you output your data and do your reports, if you would build it again, you need to find the same things. Otherwise, you have a problem because the data that you're showing to your CEO might not be correct, right? So it needs to be reproducible. That's very important. So the speed is much faster in a relational database than it is in a data warehouse. The optimization is within a query, for example, across queries. I don't actually remember what I meant with that. So the optimization is made that you basically look at what the users are doing. For example, in your database system, you look at all the kind of queries they have, and you try to build indices to account for the most frequent queries. It's probably what I meant here. And for OLAP, it's within a very big cube query that you need to execute things efficiently. Blah, blah, blah. What did I want to say? Yes, if you have a relational database, you need to back up your system. If you lose the data in OLAP, it's no big deal. You just re-ETL it. You just re-import it all, and that's fine, right? So this is also a different approach. Anyway, that's just the big summary with a bit of everything we've been seeing so far. All right. So now, it's becoming interesting. So up to now, it was just motivations. I was just explaining to you why we are doing data warehouses and how it's different from databases. But now we are getting back to the interesting thing, the actually technical thing. You remember that for tables, we've spent actually an entire week on the data model, the relational model. And we've seen these sets of partial functions with identical support and so on and so on. So that's the relational model. We've seen a lot of definitions. That's the starting point. We need to have a model for the data that we want to play with. When we have a model, we can have an algebra, so a way of manipulating that data. And then we have a query language and a full database system that takes care of that. So since it's a new data shape, it's no longer tables but cubes, we need to start all over and also define a data model for cubes. Well, I have good news, it's going to be simpler than for tables because it's actually very visual. So data cubes are multidimensional, which shouldn't be a surprise because that's what a cube is, right? It has 3 dimensions. Actually, it can have more than 3 dimensions in the data warehouse. But very often when we think of dimensions, with our eyes, we only perceive 3, right? So this is why we very often view that in terms of cubes and visualize a cube in 3 dimensions. You can visualize maybe a Rubik's Cube, right? When you, the way you turn it around, all right? Why hypercubes? Well, hyper is just a fancy way of saying that there can be more than 3 dimensions in the cube. There can be 4, 5, 6, 10. There can be a lot of dimensions. So this is why we say hypercube. A hypercube is just really just like a cube with more dimensions. Okay, so here's a concrete example. This is a cube. Imagine that every little cube here, it's called a cell. It's like in a spreadsheet cell, if you want, except it's not just 2-dimensional. There is a value in there, in every little cell here. We organize these values in a structured fashion. For example, here, I have a year dimension. This is the vertical dimension, it's the years. So I might have 2017, 2018, 2019, and 2020, right? So here I have 4 years. So all the data at that level is 2017, all the data here is 2018, all the data here is 2019, all the data here is 2020, right? It's the entire, this is all 2020, what you see here. Right, so this is a dimension. Then you have a second dimension, this time the depth dimension. So this is basically going in this direction, right? So this is the depth. So you might have, let's talk about DACH, so Germany, Switzerland, and Austria, right? Let's, for example, for a German-speaking company. So on the front, you have Germany. In the middle, behind, you have Switzerland, and at the back, you have Austria. So this is a second dimension. Where is the third dimension? It's here. It's from the left to the right, where here I might have all the phones that I sold. Here I have all the TVs. Here I have all of the books. Here I have all of, I don't know, the computers. And here I have all the tablets, let's say. So you see that I have these 3 dimensions, the year, the country, and the product. And if I take these dimensions together, they identify a single cell. So if I pick a specific year, 2016, a specific country, Switzerland, a specific product, the server, that gives me the coordinates of one specific cell, and there is a value in there. Maybe the total amount, I don't know, the revenue that came from this year, this country on that product, right? So this is the idea of a data cube, right? So this is the most important part to understand. This is the data model. So of course, I showed you 3 dimensions because this is easy to visualize, so the year, country, product. But of course, in general, there can be more. Maybe you also have the salespersons. You can sort by who actually sold it. You can sort by store. You can sort by specific product. There's plenty of ways that you can configure the data. And I hope that now it's clear that it can be more than 3 dimensions for these reasons. All right. Is it clear? Is everybody following? No questions?
No question.
All right. So I also wrote something here, fact, that's called the fact. So a single cell here is called the fact. It is a fact that there was so and so much revenue in 2016 in Switzerland on servers, right? So this is a name. So a cell, a fact, there's also plenty of ways that you can name that, but let's call it a fact. Then we have dimensions. So the dimensions is again, these things here, year, country, product. These are 3 examples. So in general, you can have a lot of dimensions. And very often it comes down to the same sort of things. So there is a time dimension that I already told you about. This is the year. It can be also by quarter, by month, right? So this is the when dimension. The what dimension I already showed to you. It's when you classify your product in several categories, and then you have all the subcategories that gives you another dimension of your cube, right? Then you have the where. This is typically organized in regions. So you can have continents, you can have countries, regions, even cities and so on, stores. You can have a currency also. It can be organized by currency exposure in a multinational company. And you can have who, if you want to also sort by the people that are in charge and that did this. So you can basically classify and categorize the data along all of that sorts of dimensions. right? Is there a question?
Yes, so a student asked if we can put everything in a 2D table with several columns.
Absolutely, I'm coming to that. That's called cross-tabulation, what you are saying. And this is why you use a spreadsheet software, actually. That's the whole point of having spreadsheet software, because the spreadsheet software only has 2 dimensions. So of course, you have the data cube, which is the model itself, which is something hard to visualize if it has 10 dimensions. In the end, however, it's a human being on the computer. So you need to actually map it to a 2-dimensional spreadsheet. And we'll look into that, exactly how to do that, the SQL queries behind that, the cross-tabulation in 2 dimensions very nicely. Right.
And why don't we use data cubes for OLTP?
I'm not saying we can't. I'm really saying this is in real life what people do. You could absolutely imagine an OLTP system with cubes. You can absolutely imagine that. There is absolutely no problem with that. It's just that in real life, people usually use cube in the context of OLAP, that's all. And in the same way, you can also imagine OLAP in the context of tables. That's absolutely possible as well. So again, this is just a weak connection that it so happens that OLTP is usually with tables, OLAP with cubes, but it is absolutely not a hard connection. You can absolutely build an OLTP system with cubes or an OLAP system with tables. Does it make sense?
Yes, thanks.
All right, perfect. So now we have a first way of doing it in 2 dimensions, actually. There's actually 2, there's fact tables and cross-tabulation. So let's start with fact tables. Well, let's get back here. Imagine this is in 10 dimensions. There is no way you as a human being can visualize that. There is a naive way of actually looking at this cube is by just looking at the facts one by one. So tac, 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 tac. I'm basically just listing them. This is then linear. It's a single dimension. I'm just taking the facts one by one in any order. Actually, I can maybe start here or start here. It doesn't matter. I'm just basically listing all of these facts. So imagine I'm taking a hammer, I'm destroying that cube, and I'm building just a tower with them. You know, like your 2-year-old. So you destroy that cube and rebuild just a tower with the little cubes, you end up with that. So this is my tower. So this is one little cube with the value inside $1,000. Maybe that was this one here, maybe, that I find as a tuple here because you recognize the table, right? So this is a tuple. What do we have? The dimensions in each column. So I have Germany, that's the country. Then I have the year here. Then I have a person here, that's the who, and I have my value in the last column. And what I have then for every row is that I have another one of these little cubes from my original cube. So you can see that here, this is just a different way of looking at that. So this is where you look at the cube as a hypercube, right? Very hard to visualize. And if you just list the facts, it's just a different way of looking at it, you get a facts table. And the power of the facts table is that it is actually a relational table. This is why we can actually use SQL to query it, but I'll come back to that. All right, so again, this is a cube that we forced to fit in a table where each column I need to do a mapping. Each column corresponds to a dimension from my cube. And one column corresponds to the value that there is in the corresponding coordinate. So for example, Germany 2016 Peter, $1,000. That's one cube. All right. Are you also following that? It's very important. The facts table is very important to understand. So this is where I'm going to stop today. So with these 2 ways of looking at a cube, either as a real cube or as a list of the facts one by one with the dimensions and the value. All right. So I'm going to stop here and we'll take it from there next week. I'm just going to quickly check that you're following. Hopefully it doesn't ask me for the password. Great. And there you go. So again, if you have any questions, feel free to ask them. And again, you probably noticed that this was very visual, this way of looking at things. I didn't throw mathematical formulas at you. It's really just a cube and then listing the little cubes on each row of a relational table. It's really that simple. I think that this is one of the reasons why these data cubes are so popular, because it's very easy to understand even by people who don't even know SQL. Okay, that looks very, very good. Very good. All right. So there's also a chapter on the book on that, but of course I'll continue next week because I need to tell you how to query that with SQL. I will need to tell you how to cross-tabulate. So cross-tabulation is what people actually do in a spreadsheet software when they are connected to the data warehouse. So we are going to look into that. All right, and that's pretty much going to be it for next week. Right. So thank you very much, everybody, and I hope you have a good exercise session today. And I'll see you next week at 2 p.m. as usual on Friday for the continuation of this lecture. Thank you very much. Goodbye.